do this later. Mava over Ka. If you recall, we have M1V1 equals M2V2, and that is the dilution equation. Oh, this is a titration equation. Now you could do this just with general stoichiometry, but this makes it a little bit easier. The Ka and the Kub, those are the coefficients for the acids and the bases. So if that were different, we would have to put, you know, a 2 maybe down there if we had a 2 in front of here. The fact that these are 1 and 1, well, that means they cancel out. So that makes it quite nice. So we have the titration of 10.68 milliliters of 0.346 molar HCl. So this is my Ma. This is my Ma. With a solution of Lish, it required 48.2 milliliters. And that is my Vub. So we're looking for the MUB, or the molar concentration of the LiSH. You plug that in. I usually like to do formulas with the variables instead of plugging numbers in whenever I manipulate them. So if we are looking for the MB, we simply divide both sides by VB. 0.346 times 10.68 divided by 48.2. Yeah, Apple Watch is not connected. I don't have my phone on me, somewhere else. So, what's up?
So the M is molarity, the V is volume. What's the C?
The coefficient from the balanced equation. Basically, what that's going to do is that's going to take care of like your mole to mole step, like moles of this, moles of that. Yeah. So that's the coefficient. For this, it was nice because it was 1 each, right? So let's see, 0.36, not 0.36, 0.346 times 10.68 divided by 48.2.
The answer is about 0.07666.
So there we go, 0.0766. 3 significant digits, so 767. And the unit for that, milliliters would cancel out, and we would get molarity left over. Any other questions that you need? How are we doing on polar versus non-polar? This back sheet right here kind of gives you an idea. The problem with this back sheet is that all of the atoms on here are like atoms. So you could have something like this be polar if, let's say, a few of these atoms were not the same. Let's say that a lot of them are H's and then you had some F's here and there spotted. Usually what the thing is with this, you look at the symmetry and then you have to sit there and say everything's got to be the same. Because imagine if we had, for example, this. You know, right away looking at that, this looks symmetrical and it looks like these two would cancel each other out. But what's the shape of this guy? Four bonds, 0 unshared pairs.
Tetrahedral.
Tetrahedral, right? So if we look at that, remember that actually is like that. Let's say that these two things right here are the Cl. Is there any pull in this direction? No. So this would be a polar molecule. Even though it looks like these two cancel out, we have to imagine this as a three-dimensional shape. So this would be polar. The fact that here they have all the same atoms makes all of these cancel out. For example, if we had Cl up here and Cl up here, then for sure, tetrahedral, remember S, P1, P2, P3, sp3. Whenever you have something like this, remember that this counts as one region. So sp2, you don't count double bonds whenever you're adding those up. And down here, right, the big one, I think we used to have this written on here, sp123, d1, d2. sp123, d sp3, sp2. How about with these guys right here? Questions on any of these terms? I think actually I had a copy of this that was better filled in than that. Yeah. That'll give us an idea of the ones that we have talked about. Boiling occurs underneath the surface. Evaporation occurs at the surface, and both of these are forms of vaporization. Likes dissolve likes. I think we actually, stopped right around there. If you take, for example, hot wings, right? Hot wings have kind of been big the past few years, getting bigger. I think they've got their own like web TV show or something like that, something ridiculous. But the hot wings, like it's based on that type of thing, the likes dissolve likes. The capsaicin is non-polar, and basically whenever you cook that wing, that skin of that, that fat cooks, and then you can put that hot sauce on there and it kind of, sticks to it or holds on to it. When you eat that wing, your mouth filled with saliva, saliva being mostly water, is polar. So it kind of like pushes that hotness all around. And you get that hotness in your mouth. That's why they serve these a lot of times with blue cheese or ranch, which also have fats, which then when you pick up the piece of celery or the carrot and dip it in there, that ranch or blue cheese then mixing around can get some of that that hot chili out of your mouth and into your stomach, which is then protected by a thick slime layer. The problem is that your anus isn't protected so well. So if you get enough of that hotness down into your stomach, then you're gonna feel it burn you twice, once in your mouth and another time in your anus. But that's the deal with this. That's how hot wings are made. Why do they have celery carrots? Anybody know why that's used? Nobody. The way that they used to do this was basically you would just get like a little paper boat. You get your wings, you get a little dish of ranch or blue cheese and celery carrots. And it was basically a way to save on having to give you utensils and stuff like that. So the celery and carrots is basically just a ranch or blue cheese delivery device to get that to your mouth. If you had like a spoon or something and you were spooning ranch into your mouth, that'd be pretty ridiculous, right? Nobody would, don't want to be the guy that eats ranch by the spoonful. Probably. If we look at the trends in we didn't talk about that one either. So if we look at these trends, let's discuss why they exist. Atomic size, that's going to be the factor with all of these trends, basically. So if we take a look here at sodium, let's just pull sodium out. We have 11 protons in the nucleus. We have 11 electrons outside the nucleus. This is the start of the third principal energy level. Each time we go down a principal energy level, we start another energy level that's outside of the previous one. So we know it's going to get larger as we go down. Now, the weird thing is as we add electrons, we see the trend that it gets smaller. So that doesn't make sense if you just think about it on top of that. Like, well, we're adding electrons, shouldn't we get bigger? Keep in mind, every time we add one electron, we also add one proton. that makes that negative charge, I'm sorry, that positive charge of the nucleus bigger. And those negative charges are then going to be pulled in tighter. Imagine like a neodymium magnet versus, one of those garbage refrigerator magnets that barely even stick to the refrigerator. So like if you try to take a piece of artwork and put it on there, it just like slides down. But a neodymium magnet has a lot more magnetic force with it. So as we go across here, this more positive charge of that nucleus, or higher or greater nuclear charge, is able to pull in. Got some problems here. Give me 1 second. There we go. It's able to pull those electrons in tighter. And that's going to be the factor for everything else. If it pulls in the electrons tighter, the ionization energy is going to be more, because it's closer to the nucleus. So it's going to take more energy to pluck that electron from something that has a smaller atomic size. The electronegativity, well, since they're pulled in tighter, it's more likely that the nucleus of that atom can then attract electrons from other things. So fluorine has its electrons put in very, very tight. So whenever it gets close to something else that's a little bit bigger, that nuclear charge that it has, has the ability to possibly pull an electron off of here. If the electrons are way out there, then if they come into contact, and the nucleus is kind of far away from these the electrons out here, those electrons are going to interact first and repel. It's never going to give that nucleus a chance to basically attract possibly another electron. If the electrons are in tight, that nucleus may be able to get in there and snag an electron. An electron affinity, yeah.
So there was a question on the review yesterday, like the unit thing, and it kind of asked, but it asked like why they're smaller, and there were two answers. One was because of the nuclear charge, and one was because it's more electronegative. Which one would that be? Because they're really similar.
Do you remember the question? It's been a week.
It was along the lines of like, it was like two ions with that would have the same number of electrons, but asked why is one smaller than the other, because like one was like 2+ and one was 1+ or something like that.
So is it calcium and potassium or something like that, or sodium and magnesium?
I don't remember what the
That sounds familiar. I think it was oxygen that was
Yeah.
2 negative and fluorine that was -1, and
I
so they
think
had
that's
the
what
same
it
number
was
of
too.
electrons.
Yeah.
But
I don't think it was plus. Thank you.
So we have O2 negative and F negative.
Yeah.
So here we have 9 protons pulling on 10 electrons, versus here we have 8 protons pulling on 10 electrons, right? So that's a decent nuclear charge thing. And so then it said that the oxygen was larger.
Yeah.
Yeah. So that would be the nuclear charge thing. The electronegativity, that's basically whenever it's trying to pull other electrons. That's that's going to be a factor when it's trying to get other electrons off of other things.
Yeah. Okay. So yeah. So they're sort of related, but they're not the same thing.
Yes, you got it. So the electronegativity is based on this fact, because it's able to, well, I mean, obviously with the atoms, not the ions, but because it's able to pull those electrons in tighter, then that nucleus has a better chance of pulling more electrons. And electronegativity, as we know, also deals whenever we're talking about bond sharedness, if that's even a term, but when we're talking about pulling electrons from other atoms, even if you're covalently bonded, pulling them closer to you. So basically, I think it's what we call like the aggressive handshake, right? Like Uncle Tom or whatever, Thomas or whatever. That's like when you're trying to sit there and grab his hand, he like pulls you in or whatever, or tries to squeeze you. That's the things with the high electronegativity. I remember my Uncle George used to do that all the time, like try to squeeze my hand, and I'm like, what are you doing? You know, like whenever I was 14 or 15, like power struggle. But that's the thing with the electronegativity. If you've ever seen that, I'm sure I'm sure you guys have seen that on something where I don't even know if uncles do it anymore, or people do it anymore, but the whole squeezing the hand as hard as you can thing. But that's what electronegativity is. It deals with either attracting the electrons or that. If you're talking about these with their own with their own size or whatever, a nuclear charge would help determine that size. Electron affinity, basically that is how much you like electrons. So chlorine again, chlorine, oxygen are going to have a high electron affinity. Same thing, it's dealing with that atomic size because of that nuclear charge we talked about. Electron configuration. The easiest way to find out what element, I got all your pictures and well, not your pictures, but your names. Electron configuration. I remember the easiest way to find out what element is being shown with the electron configuration would be to count the electrons. For example, did you guys go over like the exceptions to the weird rules of the electron? So if we have argon, for example, we're doing copper. We have argon, we have 3d10, 4s1. This is the predicted electron configuration for copper. It looks a little weird to us. We might think that this is the excited electron configuration, but it's not. Right there where that 3d10 fills up versus having a 4s2 3d9, this seems to be more stable. The reasoning behind this is because the energy level between 3d and 4s is so close to each other. But if this confuses you, if something were to say, hey, what's the electron configuration, or what element this is the electron configuration of, the easiest way to go about that would be to add up. Argon is 18, plus 10 is 28, plus 1 is 29. Now, obviously, if you were asked to make that electron configuration, unless you had that memorized to be copper, then you would probably do 4s2 3d9. It's one of the exceptions. Another exception would be for manganese. It likes to do a 4s1 3d5. So van der Waals forces, London dispersion, I would have put that differently. If we got London dispersion, dipole, then hydrogen bonding, and then dipole ion, maybe that's why, but that's increasing order of strength, strongest versus the weakest. If you're looking at compounds with this, the more electrons something has, the more London dispersion forces it has. If you have polar bonds, then you have London dispersion forces and dipole. For basically, the London dispersion forces is like a momentary dipole, or it's called a dipole moment. It doesn't last very long, but you do have the shifts in the electrons that can cause something to be, slightly more negative on one side and slightly more positive on the other side. When you have a dipole, you actually have, a partial positive and a partial negative charge on different sides of the molecule. Hydrogen bonding is when you have basically the NOF bonded to a hydrogen, and these guys pull those electrons far enough away from that hydrogen to cause a partial positive charge on it. And then if you have a lot of these things in the, in the same container or whatnot, since that has a partial positive charge, this will have a partial negative charge. And that hydrogen's partial positive charge will be attracted to that partial negative charge. In reality, hydrogen bonding is what holds your DNA together. If you recall that spiral or whatnot, when you have like the C and G, basically there are 3 hydrogen bonds that hold that spiral together. And AT has 2 hydrogen bonds. Helicase, the enzyme, actually is basically going to act like we talked about the other day, but act as a kind of almost like a surfactant or whatnot, and come in there and basically break those hydrogen bonds and allow it to be unraveled and replicated. A dipole ion, basically you have that partial charge grabbing on a full charge, and that's why it's considered to be the strongest. Usually with dipole ion, you also have a lot of these going on. Usually what you're talking about is like water dissolving ionic compounds. So you have that little water molecule dance where all of the particles are surrounded by water molecules. Keep in mind that the oxygen is partially negative charged. So if your ion is a positively charged ion, the oxygen head of the water molecule is going to be closest to it. If it is a negative, then the partial positive charge of the hydrogen is basically going to be surrounding it. Group and period names. I'm assuming you guys know this, but alkaline metals, alkaline earth metals, transition metals. This is the chalcogens. I don't think that you'll have to do that, but oxygen family, halogens, and noble gases. Lanthanide, actinides. These are called the inner transition metals. Everything with a group A is called a representative element. I think that's about it on that. That's what I got. I did get the final exam put in there. Yeah, question? Nope, momentary. Let me take a look real quick so I can tell you. I went with basically as best I could with the one that Mr. Verbrugge left. But like I said, he had like 79 questions. How many did I end up with? I ended up merging a few of the questions. Come on, you. Here we go. Nope. Here we don't go. There we go. 66 questions. So you'll have the 90 minutes to do that unless you have an individual education plan that says you get more time. The questions were only slightly edited. For example, like if it were some type of math problem, we put variables in instead of just fixed numbers, like a range of density, like a range of masses or a range of volumes if you were calculating out the density. If it was a naming compounds, I used variants of metals and non-metals versus just having like name NaCl, right? Any questions from you guys about the review guide or the final exam?
I've got a question about the quiz from last night.
Yeah.
Question 11, do you have it?
I don't have it pulled up.
Okay. It's, do you want me to like read it or?
I'll just pull it up.
Okay.
Keep in mind that some people haven't taken this, but we are grading this on completion. 75%. A 20 milliliter sample of 0.200 molar. Is that the one?
Yeah, that's the one.
So basically, we are writing out a reaction. A2Cl3 plus barium nitrate. What are we going to yield here? Concentration of barium carbonate precipitates. So we get barium carbonate plus potassium nitrate. That's going to be 2. So we got to figure out how much, basically what we have here is, and we're looking to see how much of the barium is left over, right? So 2 things, what is the final volume of the solution?
It's 50 milliliters.
All right. And we need to figure out how much of the barium did not react with this, right? So if we have 0.2 molar of the CO3, we're going to figure out from that how much of the BA would react. So let's go ahead and start there. 20.0 milliliter. Every 1,000 milliliters is 1 liter. For this, every 1 liter has 0.200 molar. And actually, well, moles, and every 1 mole of K2CO3 reacts with 1 mole of, or forms 1 mole of barium carbonate. Can you guys see that okay? 20 divided by 1,000 times 0.2.
It's 0.004.
0.004 is the moles of the barium carbonate that will form. So we have 30 milliliters of 0.4 molar. So 30 milliliters, 1,000 milliliters is 1 liter. Every 1 liter has 0.400 moles of barium. Thirty divided by 1,000 times 0.4.
The answer is 0.012.
So out of this, 0.004 moles were reacted with it. 0.012 minus 0.004.
It's 0.008.
So we have that many moles over 0.050 liters. 0.008 divided by 0.05.
It's 0.16.
So we get 0.16, 3 significant digits. Did they carry all that all the way through? 3. Yeah, I didn't do well with significant digits. Sorry about that. But we get 0.160 moles per liter.
Okay, that makes sense. But how do you know that the Ba2 plus is part of the original BaNO3 solution instead of part of the barium carbonate?
All right, so we know that the only way we can make barium carbonate is with the carbonate. So this calculation here finds out how much barium carbonate can be made because we only have 20 milliliters of a 0.2 moles per liter solution of this potassium carbonate. So this right here figures out how many moles of the barium will be used to make the barium carbonate. This right here then figures out how many total moles of barium we have anyway, of the barium ion. So since this is how much was used to make the barium carbonate, we subtract that from the total of the barium that we have to use. I think the trickiest part here is keeping in mind that you have to add the 2 amounts of the solution because that's going to be the final volume. And the molarity is moles per liter.
Okay, but like nowhere in the question does it say that barium ion is part of BaNO3 too. So how do I know that?
So your solubility rules state that barium, anything with nitrate is soluble, right? If we take a look here, anything with nitrate is soluble. I don't know if you can see that. So that means that whenever we talk about barium nitrate, this is going to be aqueous. So then if it just as if we were doing a net ionic equation, that would be Ba2 plus aqueous plus 2NO3 negative aqueous. So that right there is the barium 2 plus.
Okay, thank you.
You're welcome. Any others? All right, let's go ahead and call it because that video of me doing that, the final exam is about an hour. The final exam review guide is about an hour. So I'll let you guys take 10 minutes and get ready for your next class. I'll do the same. Unless you want to stay after, and I think that somebody, don't forget my office hours or my support hours today are from 10:30 to 11. And I know that at least one of you guys wanted to come into that, which is by all means perfectly okay. They're every day that time. If you have any questions, by all means, stay on. Otherwise, get out of here and have a great weekend. The weekend before finals. Take care. Oh, I got one of the chat things. I always forget this. Is the final open note. That's amazing, Sam. The thing is that you don't have to take the final with your camera on in front of me. So the final exam is basically intended to be taken with the periodic table that the AP periodic table and the AP equation sheet. That's the way it's intended to be taken. But obviously you're going to be on your own taking that. So that's going to be a moral choice for you. Maybe that's going to be the hardest part of the final exam. Any other questions? We can get out of here.
Thank you.
Thank you.
Thank you.
Yeah.
Good day.
You guys too. Have a good weekend.
Have a great weekend.
Thanks.
Mr. Jackson, guess what?
What?
Me and Diego got into Rose-Hulman for chemical engineering.
That is awesome.
And they said it was because of your letters.
You're kidding me.
No.
Kidding me. Or they didn't say that. Now I'm confused. They were just like Mr. Jackson or not. I'm very proud of you guys. That is awesome. Is Diego even on here anymore so I can congratulate him? No, and she left too. I'm going to close this out, guys, then, so that it will render the video.